Hello, everyone. Today we will explore digital twins, virtual mirrors of physical systems, and let us predict and prevent threats before real-world damage. We'll cover how they work, how to build resilience into them, real-world cases, and future challenges. So it's my pleasure to introduce our expert, Professor Andrei Petrovski, Faculty of Security Information Technologies research professor. So let's begin. Professor Petrovski, it's over to you.
Excellent. Before I proceed, can I just make sure that you can all hear and see me? I guess, Nikolai, if you just confirm that you can hear me.
Yeah, we can hear you and see
Excellent.
you perfectly.
Thank you very much. Thank you. Well, I'd like to start. Well, first of all, let me share the presentation just to make sure that everything works. Right. Okay. I'd like to start by thanking IT space and Nikolai in particular for giving me the opportunity to present this seminar and also to have a chance to speak to an audience. Some people present here. Thank you for your time, and some people might look at the presentation later on. So the title of the seminar, as you can see, is the application of using digital twins to ensure resilience of cyber physical systems. So there are a number of terms here. I will explain in my seminar. So you might be familiar with them already, might be not. But the focus of the seminar will be on practical usage of digital twin. So it's not a master class on how to build digital twins. It's a very lengthy and quite complex process, and I'll explain the main phases of it today. But at least you will have, if you are interested, you will have a chance to get exposed to this quite an interesting and timely topic. Because digital twins nowadays is viewed as one of the main mechanisms for so-called digital transformation. Yeah, and we'll talk about this. So to be more specific, the outline of the seminar is presented here. So we'll start with the digital transformation, what it is, why we are looking at digital transformation, why it's used specifically in industry. Then, as part of digital transformation, I will talk very briefly about cyber physical systems. My assumption is that you more or less familiar, most of you familiar with the concept of cyber physical systems, but I will give a few kind of clarifications what it is exactly meant by cyber physical systems in the context of this seminar. The focus of the seminar is on digital twins. We will look at few aspects and concepts and practical usage of digital twins. I'll start with foundations. Then we'll look at why and how digital twins are used for. Then we'll consider a few tools and platforms for developing digital twins. So if for some reason, that would be the best outcome of my seminar, you become interested in digital twins and decide, look, this is something, it's an interesting topic to explore. Then at least you will know from where to start. And also we'll look at some of the use cases. And use cases will be related to the usage, obviously, of digital twins, but they will be mostly focused on cybersecurity applications to make digital twins as tools be applicable in the area of enhancing the resilience of cyber physical systems. And I will finish with kind of a transitional topic between digital twins and another huge topic, very important nowadays, is the use of data analysis, specifically with the help of artificial intelligence and machine learning. So that's the structure of the talk. And before I start, not all of you know who I am. Just to briefly introduce myself, without giving you kind of delving into too much details. So at the moment, I have a position of a research professor at ITMO, Faculty of Secure IT. But as I started relatively recently, I started in March 2025. Before that, I was working in a university. It's Robert Gordon University in Scotland, and also it's the place. The city is Aberdeen, and also in Aberdeen there was a research institute. So it's called National Subsea Center. And the reason I'm mentioning this to you is that some of the applications will be related to marine industry, subsea industry, subsea technologies. So technologies and applications which are related to marine and subsea industry, right? So you'll see examples, but I will try to generalize the examples so that they are applicable not only to subsea industry. Subsea, it's meaning underwater. There is a historical reason why we were interested in those applications in National Subsea Center. It's because in Aberdeen is a center of oil and gas industry in the Northern Sea. And there are many oil and gas companies, operators, which obviously focused and interested in doing research in relation to subsea applications, marine applications. So that's the reason. But as I said, I will try to generalize the concept, and when we look at use cases and tools, platforms, it will be generic, so that the same tools, platforms, approaches can be applied not only to subsea digital twins, but also to other applications. Right. On teaching front, I've been kind of this semester. I was teaching MSc students. I just finished yesterday. A module, it's also a seminar series on operational technology security, or security of operational technology. Very briefly, what is operational technology? So obviously, you're all familiar with IT security. IT security is about securing data. Mostly, yes. That's the main focus of IT is data. And when we talk about IT security, obviously, you know the triage, confidentiality, integrity, availability. With operational technology, it's about processes rather than data. So, for instance, if you have a smart manufacturing facility, water treatment facility, oil and gas, drilling rig, for instance. So there is a production process. When there is a production process, the systems which control the production process are called operational, or are combined together, and they're referred to as operational technology. So the difference is operational technology is about processes, IT is about data, right? The implication of this is that when we talk about security, we're all familiar with IT security. In OT security, operational technology security, the priorities of the security requirements change. So if in IT, for instance, you have the highest priority is the confidentiality of data. In OT is safety, reliability, or resilience, and also availability of data. because when we read data from sensors, some of it is confidential, but only a small portion of it. The important thing for us, as far as if we are dealing with OT security, is to make sure that the data is coming, yes, is acquired in an appropriate way. So that's what I've been teaching this semester to MSc students. Sorry, I don't see the names of. I kind of saw Sergey, who joined us. He's doing a project with me, the MSc project, but I didn't see other names. Anyway, so hopefully it will be some of some relevance to you in terms of research. That's what we are going to talk about today. Is the main focus is cyber resilience of industrial control systems. Industrial control system is the main means of operational technology. So the systems which control industrial processes. Yes, that's one of the major areas of my research. And then as part of it, in order to achieve cyber resilience, obviously certain models and certain processes, they have to be modeled. So and the model nowadays, or modeling process nowadays, is based on data. So it's data-driven modeling. And the data-driven modeling is the vehicle through which we get information about industrial processes, and then as a consequence, we will kind of try to deal with cyber resilience of operational technology. With data-driven modeling and close association comes machine learning, in particular for fault detection and predictive maintenance. But in the context of today's seminar, the fault detection, by fault detection, I will mean some abnormal situations, some of which will be related to cyber attacks, both external and internal. And also computer-assisted measurements, but this is also part of data acquisition and using data-driven modeling. In the context of today's seminar, it will be processes related to acquiring data from IoT, Internet of Things devices, in particular industrial IoT. I've been, as in my role of researcher, my previous job was related to a number of research projects, which were sponsored by companies. And here is the names of some of the companies. Selex, now it's called Leonardo, and the company deals with drones. It's very timely nowadays. It's been developing drone or UAS, unmanned aerial systems. We refer to them as drones. Viper Innovations, this company were developing equipment and services for underwater subsea production. Net zero technology is mostly about it's green energy, and Seaflow is the company for which we were developing a digital twin. So that's so I mentioned only the companies who the line of business of which relates to the topic of today's seminar. Right. Okay. So let's switch to the subject area. So we'll start with we'll structure the presentation as typically recommended. We'll start with a broad base, and then we will focus on things which are relevant to the research areas I mentioned, and then we will look at the mechanisms, tools, and platforms for developing digital twins. And then, so we start with a broad base of critical infrastructure, critical national infrastructure. Then we will be narrowing down to the specific tools that can be helpful in protecting this critical infrastructure. And then we will kind of broad up again in the sense that we will look at how these tools can be enforced, or how they can be enhanced with additional data analytics facilities, such as using machine learning and artificial intelligence. So that's the structure. First, critical infrastructure, right? So as I mentioned, this slide is mostly about marine infrastructure, and the reason was that we were focusing on marine infrastructure most of the time. As if we take that as an example, obviously there are examples from other areas. Nowadays, in Russia, a lot of attention is given to water treatment facilities. You might know this. Also, smart grids, smart electrical grids, which are examples of critical national infrastructures, right? But if we look at in each of these infrastructures, there will be similar problems. As an example, I use the marine infrastructure. So what does it involve? It obviously involves some kind of hardware devices, installations, pipelines, cables, ports, vessels. All of these are part of this critical infrastructure. All of this, right? So previously, I'm not saying that they were not used previously. Of course, they were used in the past. But what is happening now? These systems, physical systems, they are getting augmented. They're changed slightly. So on top of the physical infrastructure, we put a cyber layer, or controlling layer which controls physical infrastructure with computer-based control systems. Yes, that's what is, and this combination of a physical infrastructure with the top layer of or cyber layer, it's called, this combination, physical and cyber, is called as cyber physical systems. So that's what I will use. That's the the semantics of the term I'm going to use today. So when I mention cyber physical systems, just imagine that you have a physical infrastructure. Examples would be pipelines, cables, ports, vessels themselves. And on top of this physical infrastructure, you put a virtual layer, a cyber layer. And this layer is used to control the physical infrastructure. And altogether, we'll refer to this combination as a cyber physical system. In addition to the usual or long used infrastructure such as pipelines and ports, vessels, there are relatively new equipment and installations such as wind farms, and also the farms which use not wind but energy of tides. Yes, which is quite popular at the moment in the United Kingdom, because there are a number of places where the current and tides is so strong that they can generate lots of energy in those places. So that's yes, I know it's the green energy agenda is it's controversial at the moment, but at least, well, in terms of technical systems, still a lot of effort is put in developing the systems. Hydrogen generation as an alternative to hydrocarbons, so it's another thing which is developing. And for generating hydrogen, again, we will use cyber physical systems, which is the physical systems, physical facilities which generate hydrogen, but also a cyber layer on top of it, which would also create a cyber physical, which would control the process. And the rest of it, I'm not going to read all of them. You can read them yourselves. The important So the informative message or the informative part of this slide is to say, look, if we take any infrastructure, especially used at a national level, and especially which is considered to be critical for the lives of people in the country, then this infrastructure will have many components. It's distributed geographically, it covers lots of area. It's heterogenic, which means that there will be different types of equipment combined together. So it will be, for instance, if you're talking about energy systems, there will be wind farms, there will be underwater cables, there will be transforming stations, so transition lines, transforming stations, lots of things. So we have cyber physical systems which is geographically distributed, which makes it controlling of it more difficult. Heterogeneous devices used in this system, and there are many other controlling problems or challenges associated with controlling these systems or making sure that they are resilient to various abnormal conditions. And the final point I want to make on this slide is that yes, okay, we can create these cyber physical systems related to critical infrastructure, but then what do we bring by introducing this cyber layer? And we bring what is called additional services. So the infrastructure becomes digital, right? So which means that there will be additional in the sense that obviously infrastructure plays a certain role. Obviously, it played it before, but by introducing this digital infrastructure, we provide additional services through IT or OT, and these services, at least some of them, will be related to providing cyber security, cyber resilience, cyber safety, and that's the purpose of today's talk. We will look at the additional services in cyber physical systems, which can be used to enhance the cyber resilience of the entire infrastructure, which we will call a digital infrastructure. Right. Okay. So, what are these services? Obviously, we are trying to introduce this digitization of industry, right? And now probably you've heard the terms Industry 4.0, Industry 5.0. Now, Industry 6.0 is starting to form. But the thing is, in short, all these new types of industries or new versions of industry, global industry, they kind of make heavy use of additional digital services, right? And these are the technologies, not all of them, but at least the technologies which are very kind of contemporary at the moment, such as machine learning. I don't need to explain what it is. Big data. Yes. So these digital infrastructures, they are now capable of generating lots of data, but without proper algorithms to analyze and process the data, all these data acquisitions are almost kind of meaningless, and they are quite expensive. You have to store this data somewhere. And then also robotics. So now the kind of terms which is nowadays used, it's a physical AI. So the AI which is aimed at kind of providing additional services for mobile platforms such as robots, drones, devices, including IoT devices, and so on. And there will be obviously optimization algorithms which are part of these additional services provided to cyber physical sensor systems. Remote sensing, it's obviously because the systems are geographically distributed, remote sensing plays an important role. When I say remote sensing, it means to be reliable remote sensing. And for reliable remote sensing, in addition to all the kind of other aspects, machine learning and big data and physical AI, you would need cybersecurity. Cybersecurity, yeah. And as we all more or less kind of work in the area of cybersecurity, but what is the mechanism for bringing this cybersecurity into or integrating cybersecurity with cyber physical systems? And the mechanism, one of the mechanisms, I'm not saying that this is the only mechanism, but one of the mechanisms is to use the concept of a digital twin. A digital twin, yeah. And next, we are going to look at what this digital twin is. But before we go into go into the discussion or more detailed discussion of digital twins, I'd like to mention what are the technologies which underpin the digital twin concept, and sometimes they are called disruptive. Disruptive. No, it's for some reason I mentioned destructive. It's disruptive technologies. Disrupting in meaning that they are kind of the technologies which change the normal operation mode. So whatever we were doing in the past, we stop doing, and we do new things. We use new approaches to provide the additional digital services, right? By the way, can I pause here for a moment? It's just what I want. I know it's not the ideal situation when you listen to me kind of through the through online session. So if for some reason you have any questions, or maybe you disagree with some things, so I would like to kind of make comments about things I'm saying, please interrupt me at any time. I kind of encourage interaction during the seminars. So it's if you have any comments, please do interrupt me. So I don't mind. I don't mind at all. Okay, so the next so the what I'm trying to say here is that in order to create a digital, fully operational, and most importantly, useful digital twin, you need to combine several disruptive technologies, right? And in particular, digital twins combine the first three technologies and try to achieve synergies. So when they accompany each other, and by doing so, they kind of amplify the effect of or the effectiveness of new digital services. And the combined technologies which create this synergy are Internet of Things, which enable getting realistic data from cyber physical systems. That's technology number one. It it was present to an extent in the past, but nowadays with the development of IoT, the amount of data, all the characteristics of big data, they come into place, such as volume, variability, veracity, and so on and so forth. Yes. But Internet of Things is enabling technology to get all this sensory data from the processes. Then, in order to create a digital twin, you would need virtual or at least augmented reality. which is displayed here on the diagram on the picture. So you have a drilling rig. So that's if you don't know what drilling rig is, that's how it looks like. It's an offshore drilling rig. It's called jackup. And by a digital twin, what we mean is we are creating a virtual copy. I'm going to give the formal definition of a digital twin, but at least now you understand. So instead of looking at or measuring, kind of combining all data coming from a physical system, what we do is that we combine all the data and form its digital or virtual copy. And then we start interacting not with the physical system, which is usually remote, located remotely, and quite the communication channels quite bad. But instead, we can work with a digital copy, right, or virtual copy, which is called a digital twin. But to create a digital twin, obviously, advances in augmented and virtual realities are needed, and they are taking place right now. We briefly talk about companies who deal with virtual reality in the context of digital twins. Machine learning and AI, I don't think I need to say much about this. So this is the technology which would enable to process and make sense of a large amount of data coming from IoT devices. There are other technologies such as physical AI. I already mentioned smart mobile systems. These are drones and kind of small mobile devices, and 3D printing. I'm not going to cover 3D printing, but these are the main disruptive technologies which bring forward the developments of digital twins. In particular, we will be interested in the synergy of the first three. Right. Okay. So now, just to give you an idea of what would be a digital subsea digital infrastructure, it's as you can see, the infrastructure is not visible. Yes. But on the seabed, there will be lots of installations. Well, I already mentioned. I don't know. See whether you see my kind of mouse pointer. I already Yeah, sorry. That's the one. I already mentioned subsea drilling systems. So these are the kind of the pieces of equipment we are going to create digital twins for. So these are drilling systems, right? And then there will be a number of other installations. So typically, the drilling system is needed to drill a well, right? But once it's drilled and hopefully you drill it in the right place, once the production starts, it's topped with what is called subsea manifold. And as you can see, a subsea manifold is a hydraulically controlled system, quite very complex. Sometimes it's called Christmas tree, because lots of various valves and so on, which could be controlled by underwater remote operated vehicles or UAVs, various deals. But that's the kind of the and in well, you can look at it as something which is placed on top of an operational well. And there will be lots of pipelines, right? Some of which are used for kind of connecting with the storage systems and transportation systems. So that's what you that's what is meant by critical national infrastructure, right? It's a critical infrastructure. Obviously, if you change this subsea infrastructure to let's say smart grid, there will be also lots of devices geographically distributed, even to a greater extent geographically, covering lots of large geographical areas. But they will be distributed first. They will be heterogeneous, so that will be of different kind. Yes. produce lots of data, and they will need to be controlled, monitored and controlled. Right. Okay. So that's hopefully I kind of explained the need for digitizing. When I say digital transformation, meaning we are bringing in new digital services. Digital in the sense that we are processing data faster. And then what we'll take is that there will be two other concepts associated with a digital twin. It's a digital object. So I already mentioned the kind of a wellhead. This is a seabed, and this is the kind of the piece of device which is placed on top of a well, right? Well is the kind of the well, it's a void through which oil and gas kind of mixture is coming up. And also a piece of important equipment is called blow-up preventer. So it's a safety equipment. So if the pressure in the well becomes too high, so in order to prevent the kind of environmental accident, what happens is that the blow up will simply kind of cut the pipes, cut and seal the pipes at this place, cut and seal it. So there will be no leakage of oil and gas. So there will be no environmental damage. So that's a piece of equipment. And we would like to have a digital copy of it. Yeah. And the digital twins will in fact be a combination of digital copies of pieces of equipment like this. Like BOP. It's quite an important one. It contains lots of devices, mechanical, hydraulic, electrical devices. So lots of things inside. Lots of things inside. And also that's the well, what is called a digital object, and we create a digital twin from digital objects. But also if we talk about digital twins, we will have a human-machine interaction between an operator and the digital twin. It looks like this. So it's a real device. This the pictures, the photos I've taken from the simulator we were working with. So that's how it looks like. So I will not explain all the details of this. The important thing is that many physical processes happening at that level, they will be displayed on this digital object. Right. So again, I'd like to pause for a second, Nikolai. I'm assuming that I will have about kind of 1.5 hours. Is it the right assumption, or correct me if I'm overrunning the seminar?
It's about 1.5. You
Yeah.
can take your time as much
So
as
I was
you want.
when I was designing the slides, I thought it would be approximately 1.5. But if you need me to kind of speed up, I will do it. I'm trying to explain things in details, but I can speed up if necessary. If necessary.
It's not necessary, so take your speed.
Okay, that's fine. Thank you. Right. So that's these are the examples of, first of all, digital infrastructure, and then the components of digital twin. Of course, this this is the drilling simulator on the basis of which we built a digital twin, right? So as you can see, it has a number of, it has a controlling station, it has an HMI, it has a master node which loads different scenarios into the simulator, and some of the scenarios, and I've been developing scenarios related to cybersecurity aspects of the operations, right? So you can develop your own kind of cyber scenarios, and Well, one of the major major use of this simulator is for training personnel. Yes. So obviously, the real drilling rig is a very expensive piece of equipment, and in order to train personnel, you need to kind of prepare people for operating the rig, and that's a good way of doing this preparation, teaching the personnel, or kind of improving their qualifications. But it's not the only one. That's why my team was kind of got involved in the digital twins and the operation of this simulator, because we were, as I said, we were introducing scenarios related to cyber incidents. So previously they were looking only at physical or engineering incidents, and we were introducing cyber incidents. And the reason I'm mentioning this is that so this digital twin can be used not only for monitoring the systems, but to look at they can be integrated with CM, SOAR systems, intrusion detection, intrusion prevention. So lots of things could be done, and these things could be done in virtual space rather than physical space. In physical space, there will be obviously heavy restrictions. Nobody will allow you to run a cyber incident on a real rig, but cyber incidents could be tested on the devices like this, on the simulators. So I already mentioned BOP, which is one of the part that's well, you see at the picture on the left, you see the top of the drilling rig, which is on the surface. This BOP is obviously under the sea, so it's underwater. But generally, what we are trying to achieve, with the use of digital twin, we are trying to build a system. Remember, the digital technology or digitization of technology involves providing additional services to the physical system. Additional services. Most of the services, they kind of relate to data processing. So this diagram shows this. So we have a physical object called problem domain. So now I'm starting to generalize. So in this example, physical data is coming from subsea equipment, but it can be something else. It doesn't need to be subsea equipment. It can be a car. It can be an electrical station. It can be various things which produce lots of data, right? Then from this problem domain, we are kind of acquiring all the data, obtaining all the data. Typically, you probably know this, in order to process it using digital services, it needs to be pre-processed, so it needs to be cleaned up effectively, and then probably normalized. And the data will be stored somewhere. And from the data repositories, we will pick up the data which is needed for our digital services. So, what are the digital services? And the digital services, well, I will refer to them as smart sensors. So these are not physical sensors. These are not sensors which measure temperature, flow rate, or kind of the pressure. These are can be different. For instance, it will be artificial neural network, which will take the data. So we can use machine learning, for instance, to build a smart sensor, and it will be trained. This smart sensor can be trained on historical data. So certain conditions, abnormal conditions, are detected or identified, and these smart sensors will recognize abnormality very fast and effectively. So that will be an example of a digital service. So building a smart sensors, data-driven smart sensor, right? Obviously, so typically in digital twin there will be not a single smart sensor, but will be a number of them. So one will be using artificial neural networks, one will be using support vector machines, one will be using statistical techniques, so one will be using, for instance, artificial immune systems and so on. The good thing about digital twin is that it provides a very versatile and very conducive environment for including all these sensors. And also, which is extremely important in applications like subsea. Remember, if you build a smart sensor once, then the operational conditions, in real life, they change. These devices, they have been in operation for decades, for 10, 20, some of them for 50 years. And of course, the characteristics of these physical devices will change over time. And again, because the physical characteristics change, we need to reflect these changes in smart sensors as well. So there will be adaptive algorithms for changing them. And these adaptive algorithms, they also use deep learning, machine learning, computational intelligence. They also can be integrated into a digital twin. And here, the device, a module, we've developed. The module have been developed. It's we call predictive engine. So what we are trying to do, we are trying to see what are the current data streams are. Okay, we are looking at data streams. Use smart sensors, pre-trained smart sensors to identify, to predict what the values are going to be. If the ground truth is known, so we compare it with real data, the predicted values with real values. And if the error is large, then we use the adaptation algorithm. If not, we proceed. So our digital twin will be copying the data we are getting from physical systems. So we have here the data is from physical systems, the upper row. Here the data coming from a digital twin, right? So if we provide this predictive engine, then in fact what we are doing, we are providing additional digital services which are in very high demand in industries, especially for critical infrastructures. So that's what we are doing. And remember, I will mention the link. So some of these smart sensors, obviously, they will be designed and aimed at identifying abnormal physical or process conditions, abnormal process conditions. But other smart sensors can be also aimed and designed to identify abnormal cyber events. As far as smart sensors are concerned, it doesn't matter. Whatever data you will train them on, they will predict the data you are using. Therefore, some of the smart sensors could be used as intrusion. Well, there will be no intrusion in these systems, but there will be some sort of abnormal. There will be abnormal cyber events. So, for instance, if an operator sends a command which is aimed at destroying a physical object, which will be considered as an attack, yeah, or manipulating data coming from the physical device, which will be considered as cyber event, and these smart sensors can recognize them, So that's the reason why we are introducing them into a digital twin. So that's what we are doing. So this kind of the theory well, not the theory. It's I was trying to explain this. That's the background. I was trying to explain to you why we are kind of bothered building digital twins, and we are bothered because we want to introduce new services in operational technology and in cyber physical systems. Now, what is a digital twin? There are a number of definitions here. I will use the last one. So a digital twin is a kind of special type of simulation model. It's not a simulation model. I'll talk about the difference between simulation and digital twin. It's a kind of simulation model that kind of presents something which happens, or examples of something in the present, such as machine or business process. Yes, it also constantly evolves, and it is aimed at monitoring and optimizing the operation of physical systems throughout its lifetime, and so on. And also the one which we probably will be using most is it's obviously a virtual copy which mimics the entire life cycle of equipment in real time. It uses modeling and other AI related services to support decisions. Yeah, so it's a decision support system. That's how it looks like. So what we have well, the important thing about digital twins is that it creates a virtual copy, a copy in a virtual space of physical equipment. Why we are doing this? We are doing this to provide additional services. And I mentioned examples of services. Okay, so that's what we are doing. That's the foundation of a digital twin. Typical architecture. So obviously there will be a physical space, there will be digital space, and there will be services. So whenever we talk about digital twins, we talk about these three columns. So in physical space, you have physical objects, whatever they are. I mentioned the ones which relate to marine industry, but also it can be electricity, water treatment, energy systems, and so on. And there will be a digital space. I mentioned industrial IoT. So these are kind of the means of acquiring data from physical space to link it to the virtual space. Yes, there will be OT systems. I mentioned them. Also, there will be IT systems. Nobody kind of cancels them out. But we are mostly interested in the process, in the process, industrial processes, which are kind of technology which are used in industrial IoT and OT. And also will be engineering solutions. So that's what digital twin will have. So we'll get all this data, and we'll try to model the system. And having built the model, I guess you kind of you're familiar with system modeling in general. Once we build a model, we can provide certain, using this model rather than a physical object, we can provide additional services. And examples of additional services I mentioned on the previous slide. I meant on the previous slide, I mentioned these smart sensors. So these are the services most kind of we'll be focusing mostly on, right? So that's the foundation of digital twins, architecture of digital twins. What are the main features of a digital twin? So you might ask yourself, or you might ask me, right? So we are familiar with simulation models. They've been used for ages. So simulations they will be used forever. What's the difference of a digital twin in terms of a simulation model? That's a summary of the difference. So you develop them and then you use them. And if there are certain changes in the operational conditions, you'll have to build a new simulation model. So that's what static means. Digital twins are dynamic, and I showed you example that certain algorithms can be used for adapting smart sensors to changing conditions. Typically, simulation model is run offline. Digital twins can be run in real time. I'm not saying that it always happens, but the potential is to use them in real time. And probably there are other differences, but probably the one which is important for us is that a typical simulation model allows you to see what can happen in the system, to run what if scenario. What if? So if we increase pressure by 15%, what will happen, right? What will happen to the production rate, to the flow rate of the oil and gas and water mixture? Here in digital twins, what you can do is that you can, it allows you to see what is happening in the system currently. So what condition, under current operation conditions, what is actually happening? And that's much more important, because if you see what is actually happening, then the reliability of the digital services you provide as part of a digital twin becomes much better, much better. Right. Okay. So now we know, hopefully, and understand what the digital twin is, why it's used for, the reason why digital twins have been created, and the reason. This slide tries to answer a question: why these digital twins are used at the moment, and the reason is that the digital twins enable this transition from data to services. Data is not new. Simulations not new. What is new is the services which are provided by the digital twins. Examples of services I mentioned: smart sensors. So sensors which process lots of data, yeah, and can be trained, can be adjusted if necessary. So they are kind of almost intelligent sensors. Yes, I don't like the term intelligent sensor, but it's still they have certain they have additional functionality, right? But also in the process of this transition, what is happening is that we integrate number of levels within a digital twin. So at the level zero we have raw data. Well, we will not go anywhere without data. Yeah, and a digital twin from a raw data we can get structured data. So that's what was referred to as data pre-processing. So from raw data we are getting structured data. Then from structured data we build models based on data. Having done this, having built the models, right, what we can do is we can see how the data flows. So in particular, if we use the Internet of Things technology, we can see what we measure, and then how the data measured is processed. And then we can integrate these services into the production process and achieve better interactivity with the system, because it's much easier to interact with the digital twin rather than with a physical system. And finally, probably it's level 5, we can achieve automation and sometimes autonomy. Autonomy meaning that the human is not present there at all. Automation means that certain operations are done without a human, but not all. Autonomy means that the human not even approaches the system. This is probably kind of a future step, but automation is kind of is applied extensively. So that's the purpose. We are trying to get this transition from data to services. And digital twins help us in achieving this. Okay, practical. So the idea here is to we use the digital twins to have practical effects or practical benefits of using this technology. So again, so what we have here, we have this duality between physical and digital spaces, right? And so the purpose is that we have the physical system don't kind of typically it's not us who are building physical systems, but typically what we are involved in building a digital or virtual copy of a physical system and integrate them together. By integrating, I mean exactly what I've been talking about. It's the provision of more advanced, more intelligent, and more kind of practically oriented services, digital services. And probably kind of this technology, just to summarize, the aim of this technology is to provide an opportunity to live in the past. It's not my phrase, it's taken from this symposium. To live in the past, meaning that we train the services, the smart sensors I mentioned, based on historical data. So we live in the present. We learn from the past, so building on so live in the present, meaning that we can see what is happening right now. What is happening right now? We learn from the past, which enables us to use machine learning techniques and trained on historical data as an example. And as a result, we can more effectively predict the future. That's the purpose, right? That's the purpose of a digital twin. Not only security related, general purpose of a digital twin. Right. Okay. So that's the background. So the foundation of digital twins. So now let's switch to the means of building digital twins. And of course, we are not new. There are many systems, some of which have been used forever. So you might be familiar with any logic systems. It's a very good simulators, and you can build digital twins of factories, enterprises using any logic. Arena, which is mostly kind of aimed at building functional models of industrial processes or production processes. Enterprise dynamics used mostly for logistical applications. COMSOL, multi-physics, and SolidWorks, it's for building the static, what I call static models of complex physical equipment. So these can be used as modeling tools to start building a digital twin application. You have to start from somewhere, right? But these are generic ones, okay? So they've been used forever. Most of them are proprietary, expensive for individual usage. Some of which are not, but now I'd like to mention the platforms which we used as well for building the applications for marine and subsea industry. So kind of just go back. So these are the generic tools, and here what we have the specific tools which were specifically designed. So the purposefully designed to build digital twins. one of which is a Digital Ocean Canada. These are, again, the reason I wanted to show you is that show you this diagram is to show that what are the typical components of a digital twin. So the development happens kind of in a in continuous way. So the platform is built, then a simulation software is built. So that's these are the stages I mentioned already on the main diagram. So it's data pre-processing, then data modeling, then building the services, and then virtualizing the services. So it's a stage process. And the process, another reason I wanted to show you the diagram is that it is staged and complex. There will be many companies involved in it because it's quite challenging to develop all components of digital twin if you are talking about serious critical national infrastructure. If we talk about that, then obviously there will be many companies involved. At sometimes different stages are assigned to different companies. In particular, as an example, for the using of virtual and augmented reality, we use the company GRI simulations, which were kind of responsible for building this virtual reality interface. So the idea here, without delving into details, so what we have here, you have this cable, right? We have this the platforms. Typically, this pipe goes to the surface vehicle, but also it's a cable gets connected to this pipeline. And for as an application, again, this is an engineering application, it's not a cybersecurity application. We can calculate, and it has been done. It already not by us, but has been done. We can calculate the tension vector at each point of the cable, and this is good because then we can predict the places where where this cable can break. Similar things, GRA simulations, when you have a pipeline on the,
Sorry for the interruption.
yes,
Your presentation is not on full screen. Prob-
apologies.
Probably we can't see the slide you want us to see.
Can you see it now?
Yeah, now it's okay.
Now it's okay. Right. Okay. So I was talking about so these GRA simulations. So just go briefly to the previous slide. So that's the company who specialize in developing digital twin, and the development is phase based, and a large number of companies specializing in particular aspects of digital twins are involved, and one of which is GRI. And GRI, they are kind of specialized in developing virtual reality and augmented reality. So this virtual reality, so this is kind of we are talking about virtual digital twins. Therefore, they exist in a virtual space. But the additional services I mentioned here, they are engineering services, such as, for instance, if you look at this cable, it's very long, and so by pointing to different pieces of the cable, you can immediately see, you can model the stress level at each piece, right? And by doing so, you can predict the most likely breaking points. Similar, if you have a pipeline like this, right? So that's the kind of the chain, also breaking points of chain. That's actually, you can see an element of a chain which is about to break. Well, in this case, nothing wrong with it. But if red color becomes predominant, That means that this piece of chain is very likely to break. Pipelines. In pipelines, the most important thing is to get to detect leaks. That's the pipeline, yeah, to detect leaks. And this is a ROV I mentioned, so it flows above a pipeline and is detecting leaks. So what I'm saying is that there will be a physical ROV, there will be a physical pipeline, but then also the data coming from physical pipeline and physical ROV will be coming to digital twin, and we will see it. We can monitor it much more conveniently, but also we can start predicting things using our digital services. So if, for instance, ROV detects a piece of rust or a piece certain interval of corrosion, then we can start examining it more closely with respect to possible links. So that's, as you can see, just to demonstrate you what is involved in developing fully fledged digital twin of subsea infrastructure. Bentley systems again. So the point I'm trying to make. I'm not going to explain all the components. So what we have here is that what happened in the past. In the past, Bentley systems looked at data repositories, and data was supplied to the clients, just in its very sometimes even in a raw form. But even if in a pre-processing form, it would be a responsibility of a client to see or to analyze the data. Instead, what we can do is, and it has been done by Bentley's, through this kind of IT infrastructure. So they don't deal with OT, but with IT infrastructure. They build virtual models of the data and then use predictive analytics. So the clients see not raw data, or not the data itself. Instead, the clients will see data in processed format. So in fact, here the digital twins are used as decision support systems. So we can reach the point when the clients don't need to look at the data, only on data which kind of only a small portion of it which is responsible for a particular event, right? So that's another example of a company building or specializing in building digital twin, but they are mostly specializing in building platforms for developing digital twins, which use simulators and the cloud infrastructure. Now these are big ones. If you become interested in developing a digital twin, you can start with relatively small scale systems. For instance, there is an Eclipse Ditto project, and this is a good environment to build small digital twins on relatively small IoT devices. So that's again, if you are interested to know more, so these are IoT devices. These are kind of modules responsible for interconnecting this device with the kind of physical or not physical, the device twin platform, and then the solutions will actually be the digital services provided for monitoring a particular system. For example, and this one was used for monitoring a beehive, when kind of certain amount of honey was produced or certain conditions of bees have been detected. That's an example of a smaller scale digital twin. That's another example. This is already in relation to operational technology. So here we have a production line. It's a toy example. So it's the point here is to look at boxes used for well, containers for parcels. And the process monitors the quality of the boxes. So the point here is that we can monitor the devices. So these are robotic arms. From these robotic arms, data is coming to the digital twin, and digital twin will store the data obviously in the cloud. Not obviously, but it will store the data. All data repositories are in the cloud. And here, what we have a module. It's a machine learning module which predicts the boxes of poor quality. So it detects anomalies based on the information coming from robotic arms. So as you can see, these are examples of introducing digital services into the system. Next one is probably that's the cybersecurity related. So now this is probably aimed at you, as if you become interested in using digital twins for predicting certain or for detecting, predicting, or monitoring security events. That's an example of a system which actually was designed for doing this. So it's a printed circuit board. It's not produced by us. Actually can buy it from the internet. It's about, well, the cost is about $40. So it's well, that's the kind of the already exists. And I think what I wanted to mention is that we are planning at the faculty. Planning to build a lab which will be, or create a lab which will build digital twins. And this is an example. So if you are interested in doing projects or in doing certain research related to this area, just let me know. So what it does, so this, with this PCB, what we can do is we can build a digital twin of a PLC. So we have a physical PLC. Actually, we also, this is a picture I've taken. This is the kind of PLC we've bought. And this is a physical PLC. And this printed circuit board is the base for creating a virtual or digital twin of a PLC device. And the digital services which are provided on top of it are listed like here. We can change the states of different input lines using relatively straightforward GUIs. And what is good about it is that it enables to run certain attack scenarios, such as flooding the network buffer, password attack, fuzzing Modbus. Modbus is an industrial protocol, and also man-in-the-middle attack. So it's a good platform for creating attack scenarios in a digital or for a digital twin related to cybersecurity and cyber resilience. So these are existing platforms and tools. And now I'm going to the use cases. So I'll probably need 5-7 more minutes. So just examples of the cyber-related attack scenarios. So first example is DOS attack. I don't think I need to explain a lot about the DOS attack. So here we developed a drilling rig. The drilling rig, it's a virtual, it's a digital twin of a drilling rig. And then we look at some of the model some of the bot attacks. So there will be bots on additional systems. The attacker will launch this bot attack, which will lead to a DOS attack on the rig, which will make data from the rig not available. Well, you know what DOS attack means. So this is kind of a breaking the constraints, the data availability constraint, yeah, which is also relevant to operational technology systems. So that's one scenario which we run on our digital twin. The second scenario is the supply chain. So obviously, kind of when we talk about real drilling rigs or any other physical system in the production process, you need to provide the system with certain material to maintain the production process. It's called supply. Yeah, if there are any supplying threats or any infected, if you are talking about software supplying, infected software, this can also be modeled through digital twins. So it's essentially the check whether the software is good or not, right? Software security. System control security. So this is related. So that's the one we used. Based on the data coming from the production well, we can see whether there are any operational conditions which are abnormal and require very quick response, very quick attention, right? So that's the use case we were specializing in. This our digital twin was developed for seeing any challenge or any difficulties, any abnormality in the system control. And some of the abnormalities, as I mentioned, they are cybersecurity related. One scenario is that when through a team viewer, it's a good example. In fact, it happened in real life, not with our system, but in real life. One of the rigs was attacked through a team viewer because team viewer was installed on the engineering workstation. And then the production facility was controlled through an engineering workstation, and various process controls were changed. We can run this scenario through, and also ransomware. Again, this is another attack scenario which can be modeled through the use of digital twin. And the last slide I wanted to show you is now now we are going we are starting to widen up. Yeah. So okay. So now we discussed what a digital twin is, how it can be used, right? The benefits of using digital twins, including the benefits of analyzing scenarios which are cybersecurity related or aimed at enhancing cyber resilience of physical systems. Now, what else can we provide? How can we do it better? So with digital twin, we will have lots of data, pre-processed input stream, yeah? And based on this pre-processed input stream, we can start identifying, classifying, and predicting various conditions related to the production facility, including the identification and classification of attacks, cyber, or to be more general, cyber events. So we can identify cyber events, then we can identify that something is wrong, right? So the identification is the kind of first stage. So we can see that something is not normal. So there is a command which shouldn't be issued at this time. That's the identification stage. Then having identified the presence of a faulty condition or a security event, then we can classify this security event based on possibly additional data. So as you can see, we have here, so we identify a security event on the basis of historical data. So that's the way how we build smart sensors. Then additional data will be needed to do the classification. So at this stage, we simply say something is wrong. Here at the classification stage, we say this is what is wrong is this. We are dealing with a system control attack or system control abnormality. So this classification will issue a specific alert, and then we can actually have a prediction phase. So based on this cyber event, we can predict what is going to happen. If the cyber event is not too dangerous or too risky, then probably nothing can be done or nothing needs to be done. If it's on the other hand, it's very risky, so we can at this stage between classification and prediction, we can introduce risk assessment and risk management as additional services, digital services. The purpose of digital twin is to provide these services. So as a kind of conclusion, we can, through the introduction or integration of these phases within a digital twin, we can achieve better system resilience if we talk about cyber events, and as a consequence, safety of the operation of our digital infrastructure. Right. Okay. So that's the end of my talk. I have listed a few papers, relatively recent papers, written mostly by our group. So if you are interested, you can find more information about the use of digital twins here on the slide. And that's the end of my presentation. Thank you very much for your time. Ready to answer any questions.
Thank you very much. It's really interesting topic. I have a question. So you mentioned that digital twins could be used as a tool for educational purposes. Could you explain a little bit better, a little bit more about it?
Absolutely, absolutely. In fact, I'm very interested in as I mentioned, the digital twin we were operating. So we use it for two purposes. The first one is to introduce cyber scenarios and to see what can be predicted through running these cyber scenarios. That's number one. But number two, and that's the main function of the simulator, is to teach personnel, right? This because now it's a digital twin, so the scenarios we can run, they are all based on the data, and as such, they can be relatively easily to integrate into the set of existing scenarios. Now, if I interpret your question correctly, I didn't see who asked it. I assume it's you, Nikolai. The cyber range, right? So the cyber range you have at ITMO in the faculty. Now I know that there are certain scenarios that can be run on a cyber range. So what can be done is to add new scenarios related to, let's say, cyber incidents in operational technology, cyber incidents in not in IT infrastructure, but related to, let's say, operation of physical equipment, including the equipment which is used to control physical processes like PLCs. So the last example I gave, the last example I gave with SIB ICS. So that's the quite a large, nice platform to run some of the simulation scenarios, such as, for instance, man in the middle attack, man in the middle attack for industrial protocols like Modbus, Right. So if you are interested, then we can actually have a more detailed conversation. But the point is probably that's the how we are going to run how the digital twins can be used in educational process. That's the question you asked. And the answer is by developing and introducing scenarios which we would like to explain in the education process.
Yeah, thank you very much.
And the platform of CyberRange is great for this.
Yeah,
So
that's correct.
it already exists. The question, the task is to create this scenarios.
So this is the most complicated from my point of view. The most complicated part is to how to integrate the digital twins into the educational process. Obviously, we can create somehow the some some instruments and some tasks on our platform, but it's because digital twins is the uh, uh, really precise copy of the processes and data flow of the real cyber physical systems. It's a little bit more complicated than just to create some task for network flow or just AI data, etc. So
I see your point exactly. Well, that's the one of the disadvantages of digital twins is that you're right. Typically, it involves heavy modeling, lots of data, lots of virtualization and virtual reality, augmented reality, and rest of it. So if we talk about a relatively small group of people who want to build a digital twin, sometimes the task is prohibitively expensive and time consuming. The solution to this is that, as I said, you are right that kind of in for practical usage, digital twins need to be realistic. The more realistic they are, the more useful they are. However, for educational purposes, and this is something I'm thinking about, for educational purposes, you can build a simplified digital twin only to demonstrate, sometimes even demonstrate, sometimes maybe model, but using straightforward modeling techniques, simple processes. If that's the case, then all the complications of digital twin does need to be involved in the process. So it's possible to build a basic digital twin designed for only specific demonstration or educational purpose. If you ask me, have I done it before? Not, but no. But I will be very interested in doing it myself. Obviously, if there are people at in the faculty in our group who are interested, that's the purpose of the seminar. Let's find interested people and collaborate.
yes, thank you. Sounds good. And you are correct. The simplification is probably only one way to create
Yes. Mm-hmm.
for reasonable time and resources the version of digital twin simulator for the educational purposes. So
Yeah, I think
thank you very much.
what interests me, you see, the picture I showed you, the PLC we bought, and also the so it's semantics PLD, a PLC, and also the printed board ICS. This will be that's all what is needed as a physical platform. That's all. Then everything else goes on CyberRange, for instance. And then on the CyberRange we run. Now I know better how CyberRange operates. Yes, there are restrictions, but maybe we can implement certain attack types on the industrial protocols, and then it will be, yeah. So the answer is simplify it to the limit. There will be a limit. After the limit, then the scenario becomes useless. But if you simplify it to a practical limit, then it still be, for especially for educational purposes, it can be useful.
I see. Thank you very much. And we have more questions, especially in the chat, I think.
Okay, I can go through the questions in the chat myself. So Nikita asks, is it possible to get the presentation after the seminar? Yes. The presentation, that's for you. That's for the group. I will forward it to Nikolai, and Nikolai, whatever means you use for distributing this. So the presentation is available.
Yeah, we will attach the presentation to the video recording, and you can watch the video recording
I
and
have the PDF file, so it's easy with PDF. So I will have it.
and in the description to the video, you will see the link to the presentation.
So the answer to the question, the first question from Nikita is yes. Then Nikita thanks me. Thank you so much from Furkan. Thank you for your time and for your interest. And Shubham also thanks me. Sergey asked whether it's possible to do it in Russian or to watch it in Russian. I have to re-record it in Russian then. But Sergey, if you are interested, Sergey is one of my MSc students. I can, one of the meetings with you, I can briefly run it, highlighting the most important things for you individually. I don't see any more questions.
So, do we have any more questions? You can ask via your voice, via microphone freely, or typing it into the chat. So please.
Okay, so while you're thinking, just final kind of summarizing point. Of course, this is a huge area. Digital twins. Many people argue. Many people don't like the term. Many people compare it with simulators, and then introduce certain gradation, such as digital objects. So this is simply a representation of a physical object in a virtual world. It will have no link to the physical world. It's called a digital object. Then there will be digital shadow. A shadow will have a one-way link, so it's coming from physical to virtual. Data will come from physical to virtual, but cannot go back. And digital twin is that when we have two-way communication, so it's the data coming both from physical to virtual, is analyzed in the virtual world, and then sent back. Certain commands will be sent back, or maybe certain instructions or certain alarms if there is an abnormal condition. So that's the digital twin. What is the important? So what I'm saying is that some people argue that it's not new. This concept is new. It has been existing forever. Some people say that this is similar to a simulator. Some people disagree that it can be useful because there will be always assumptions, always simplifications, with which in majority of cases render digital twins not useful, especially in critical infrastructures. So when one mistake can be fatal, right? What I'm saying, kind of the argument I'm trying to make, and I'm trying to convince you, is that digital twin is a versatile platform, as the kind of universal platform for introducing certain digital services. So with industry digitization, it means that we are introducing new digital services. And digital twin would be a very good means, very good vehicle for providing these digital services. So if you are interested in this work or this type of projects, what why is it what is the main difference? The main difference is that you are using both physical systems, so then you're kind of dealing with the engineering world. You have virtual systems, you are dealing with computing world, and with effective data communication between the two, and also decision support based on the new digital services. Now, if you consider the big data developments, if you consider optimization, if you consider machine learning AI, all of these can be combined, can be integrated, or can be provided as a digital service within a certain vehicle, and that vehicle is a digital twin. So I see the main purpose or the main benefit of a digital twin is a vehicle for providing additional digital services. So if you're interested, just let me or Nikolai know, and we'll see what can we do in terms of progressing this work forward.
So I think we have no questions left.
No
So-
more questions. That's again. Thank you very much for your the time you've spent.
Oh no, we have one
there is
question.
there is a question. Furkan, Polytechnic University. Oh, you have a strong team there who deal with digital twins. What? But we are interested in collaborating with the Polytechnic University. What will be the role of artificial intelligence and physical AI in future digital? Okay. The role the role Furkan is, as I said, the provision of additional digital services. So if we talk about smart sensors, so the sensors which process the data, okay, you get a huge amount of data coming from an industrial plant. You won't be able to process the data yourself, right? So you need an AI agent. Now it's a popular term, AI agent, to do the data processing. Otherwise, you won't be able to process the data at the speed the data is coming towards you. So that's the application number one. So for more effective and timely data processing, that's what application number one. Physical AI. So if you have a robotic system, the robotic systems operate in real time. Okay, that's another example where you need a very fast response, extremely fast response. That's the use of AI. So I know for instance, if you use machine learning for detecting faults, it takes lots of time to, let's say, train a neural network. But once it's trained, it can recognize certain things very quickly. It can operate almost in real time. Well, sufficient for robotic systems or physical AIs. And then if you consider the security aspects, cybersecurity aspects, now, as you know, the attackers use AI tools, so they don't launch attacks manually. And some of the systems nowadays, the attacking systems, so they kind of enable this automated reconnaissance and automated weaponization. So it's lots of help is coming to the attackers in terms of identifying vulnerable systems and attacking them. So in order to mitigate AI-assisted attacks, you need AI-assisted defense tools. So that's another role if we are talking about cybersecurity aspect. I don't know whether I answered your question or not. You can type in. So there is another question from Nikita. Digital twins may be used in. Okay, that's fine. Thanks Furkan for your question. Nikita asks, so digital twins may be used in every digital product. Yes, Nikita. The problem is, of course, is that as we discussed with Nikolai, digital twin is not a cheap tool. That's the problem. It's not cheap. So if a digital product, digital products, kind of lots of digital products, and some of them are they don't render digital twins necessary or effective, cost effective. Theoretically, yes, so every digital product can use a virtual representation through a digital twin. Yes, theoretically. The question is, do you need a digital twin for certain products? Maybe certain products are not complicated enough to use the digital twin. That's my answer. Great. Okay, good.
So now I think that's all. Thank you
Excellent.
for
I
your
think we are in time, Nikolai. So it's
yeah.
4 minutes to 8 p.m. So good. Once
So
again, I'd like to thank you all for your participation. Hopefully, or I hope that I managed to at least expose you to some of the problems, challenges of developing digital twins, and most importantly, the benefits of using digital twins. So if you become interested in the area, that's I will achieve my purpose. Thanks again, and kind of I wish you pleasant break and pleasant New Year break. So it's almost a Christmas lecture by me, Nikolai. Yeah.
Yeah, that's correct. And a
Excellent.
really good one, I'd say.
Good. Thank you.
Thank you
Thanks.
very much. Have a
All
nice
the best.
evening.
Bye bye.